Okay, so we left off last time seeing some of the ways that Newton's method could go wrong and looking at it in one dimension where we could try and get some intuition for what was happening. So let me pick up there and we'll look at another example of divergence. So the one we saw last time, I guess, was at least one of the things we might have seen too, I'm sort of forgetting, was we saw that it could actually start heading uphill as opposed to start heading downhill if there was a maximum and a minimum in the relevant area in which based in terms of the starting value. So the other thing I wanted to just point out was what can happen sort of more generally as the gradient gets basically as the gradient levels off. So here's an example. I'm trying to draw out f prime and f double prime for this example that I'm going to do in the demo code, where we'll see that depending on the starting value, we could either converge to the minimum or start diverging. So here's f, and I've tried to draw it such that once we get out here, this is just a linear function. Okay? And so if I then draw f prime, well, the gradient in the middle is 0. It's positive here, but the gradient basically stops changing at some point, okay? Because it becomes just a linear, it just becomes linear here. So this is not getting increasingly steep as would a fully convex function. And then if we look at the second derivative, then it looks something like this. Eventually, when you get out towards the tails of this particular part of the domain that I'm looking at, the second derivative is 0 because the gradient is unchanging, is flat. Okay. So the question is, if we had a situation like this, what would happen to Newton's method if we tried to run Newton's method from different starting points? Okay, so I've created f prime, which is the first derivative, and f double prime, which are the second derivative, as functions. And looks like I just have this parameterized by some other thing, theta, that I think I'm just using as a constant. But the question is, can we optimize with respect to x? Okay, so that's what that is. And then suppose I take x0 to be 2 as my starting value. Okay, so I'm just going to do Newton's method. I'm going to apply the Newton's method recipe, which is what's the current value minus the gradient divided by the second derivative. Okay, so that's going to get me my next value, and then I'm going to just walk my way from there. Okay, so if I basically print out what happens here, I'm just printing out this was my first value. It was at 2. This is sort of scrunched in here. And then what happened was I went to the second point, which was down here. Then I went to the third point, fourth point, fifth point, and I started to zero in. So what was basically happening with Newton's method here is because of the value of the gradient here, I basically overshot, and I went to the other side of the optimum. So I started out somewhere here. Instead of in the example we saw last time, the sort of toy example I just was drawing up, I sort of went like this, and I was walking like this. But in this case, if I start out sufficiently far up here, I can actually cross over the point that I'm trying to find and come to some point here. And then the 1, 2, 3, 4, 5 there is basically I'm going 1, 2, 3, 4, 5, 6, and I'm zeroing in on the optimum point. So that's fine. That it's fine that I overshot. It did converge to the minimum here. But the next thing we'll see is that I can actually start out with a very bad value. And one of the critical points to realize here is the good value and the bad value here are not so different. So I start out with x0 being 2 in this example, and I did converge. But if I start out just a little bit further to the right, if I start out at x0 as 2.5, then what happens? Well, then I start out, this is my starting point. I'm still crossing over and going sort of overshooting. But in this case, I overshoot enough that 2 is actually further away from the minimum in this direction than 1 is from the minimum in this direction. And then when I get to 2, it overshoots even further to the right and goes back to 3. And I basically start bouncing back and forth, and I basically diverge away from the optimum. So what's basically happening here is if I start far enough out here, then what do I do? Well, I draw my tangent line, and I follow my tangent line out. And if this thing is shallow enough, then I actually get further away over here than I was at my starting point. Okay. So I'm further away. This is further away from here than this is from here. And then depending on what the gradient is here, in this case I set up the function so it's symmetric, so it sort of causes, in part that's what causes this to happen. But here I'm at an even shallower gradient than I was here. And so now if I draw my tangent line here, it's going to go way out here before, now I'm sort of getting onto the other plot, but if I extended my plot out, it's going way out here. And then if I went up here, this is even shallower. I'm going to diverge all the, I'm going to go all the way over to here, and things are just going to blow up. Okay. And we can see that that's happening when f double prime is getting close to 0, which is not surprising because we're dividing by the second derivative. You would expect that if we could start getting values that are near 0 or small there, we might have problems with the resulting next iteration of our algorithm getting it to be an increasingly large value. And you can see that what happens in the actual numerical values, we go from 2.5 as our starting point to minus 3.55 to 13.8 to minus 50,000. So we're starting to get, it doesn't take very long before we get very far away from the true value. And then by the 6th point, I'm at infinity, and by the 7th point, R is not even allowing me to get, is not even giving me back infinity. Somehow it's overflowed in some fashion such that I'm getting something that's not even a number. Okay, so any questions about that? So in some sense, I haven't been very smart about what I'm doing here. I've sort of followed Newton's recipe. But could anybody have a suggestion as to how I could take this and not be so blindly following Newton's method that in terms of having these problems? Yeah, go ahead.
Could you just put some sort of bounds on the other side where you say if you already know that optimum is going to be in a certain range, just bound it.
Okay.
Crosses that, so.
Yeah, so that's one idea, is if I know the minimum is within this range, once I get outside it, there's no point there may be no point in continuing, and it could diverge like this, so I may not get back into the interval. Another aspect of this is as soon as I get the first and the second point, well, based on the values of the gradients, I know my minimum should be in between the two of those. So then when I get the 3 that's out here, it's silly for me to accept that 3 and continue going with the algorithm in the same fashion and just blindly following Newton's method, because I know that this is outside the range of the first two values, so something must be going wrong. So what I could do is I could do 1, 2, and then like, oh wait, I start to get to here, I realize something's wrong, so I might then go back and say, well, what I really should do is between the 1 and the 2 values, start searching in here. And I could, for example, use bisection or one of the methods that we've already talked about that don't use derivatives to try and then sort of recover from the problem that Newton's method is introducing. You could also presumably notice that, remember, we're trying to do a minimization problem. So what happens, I select my value here as my starting point. So say I'm somewhere here. And then in this symmetric problem that I was doing, what happened? I went out here, I got further out here than relative to the minimum, I'm further out here than I was to start with. So I'm presumably further up on the curve here. Well, that's a little bit silly. I'm trying to do a minimization, and my second point is higher than the first point, and yet I accepted it and just tried to continue on with the algorithm. Right? So another possibility is I say, okay, here I go here. I find that this is the next value that Newton's method would say, and I say, wait a minute, I can be smarter than just blindly following Newton's method. I could, for example, this would be called backtracking. I could say, here I'm here, this is my next point, this is actually higher. Let me start moving backwards and see if I can find a point that's actually lower than the point that I started at. So these sort of strategies of making sure I'm in the interval, if I've got the previous 2 points, making sure the next point is in the interval and making sure that the next point is actually lower than my current best estimate of the minimum, basically are ways that you can do what's called sort of safeguarding of Newton's method to avoid some of the problems that can arise with it. So I guess in summary, I'd say sort of if Newton's method is working, it's going to converge really fast, but it has these dangers that it could diverge and have these problems. But there are ways that we can be smart about basically safeguarding it so that we try and avoid some of these issues. Okay, I had another example here, which was basically this idea that we might climb uphill instead of climbing downhill, and this was just with a cosine function that just is a wave function. But we basically talked through that last time, so I think I'll skip that here. Okay, so where am I here? All right, so let's talk a little bit about monitoring convergence. So basically, the idea is we want to figure out when to stop the algorithm, right? We could just, if we could go infinitely on and trying to get increasingly more digits of precision. We know that on a computer we're gonna have a limitation in the number of digits we can hold anyway. And at some point, when your estimate is that xt is 1.34567 and xt plus 1 is 1.345676, things are not changing very much, and you should be able to see that. So in terms of how you might go about this, well, one possibility is we know we're trying to find a place where we're trying to find a root of the derivative function. So we could monitor our estimate of f prime, and we could see if it's getting very, very close to 0. And when it gets sufficiently close to 0, we could call things off and say, I'm done. I've basically found the minimum. The danger in that is basically, suppose my function didn't look like this. Suppose my function was sort of flat and look like this. Well, I might find that f prime is pretty close to 0 when it's out here, but that might actually be fairly far away from the actual minimum that I'm searching for. So there's a bit of a danger in using f prime itself and seeing whether f prime is approximately, so I have some xt and then seeing whether f prime of xt is approximately equal to 0. So the more standard thing to do is actually just to look at the string of values x1, x2, x3, x4, xt plus 1, and see if xt and xt plus 1 are really, really close together. And if they're sufficiently close together, then call things off and say, I'm done. I've gotten my answer to enough precision. So we could say, okay, is xt plus 1 minus xt, is this difference sufficiently small, less than some epsilon, for example? Often, since we're talking about numbers in a relative sense, what matters is, am I relatively close, not am I close in terms of the absolute value of the number, or of the difference. So I might look at relative convergence and normalize relative to the size of the kinds of numbers that I'm working with. On the other hand, if my xt, if the minimum of the function is occurring near 0, then I might be dividing by a number that's somewhat close to 0 if I do this. So that could be a problem. So the sort of thing that people will often use is something like this, where I take the difference between my current estimate and the previous estimate, divide by xt to scale things to be on in relative terms, but also add on some epsilon to make sure that this denominator is not too close to 0. And we want to also account for the fact that we only have a certain amount of precision on a computer. We know about machine epsilon. So one thing that one sort of standard thing to do is to take epsilon to actually be the square root of machine epsilon, so to be something like 1 times 10 to the minus 8. So that's a fairly standard thing to do. And if you look in R in the optim function, which we'll talk about in a day or two, you'll see that there's a rel tal argument, and that's basically what this quantity is. That rel tal in R is this epsilon that we're talking about choosing here. Okay, the other thing that will generally be included in any optimization function is not just a metric for what's the tolerance by which we decide when we've reached the minimum, or close enough to the minimum, but also a maximum number of iterations. So that if we're in a situation where the estimate is not actually converging, it might be diverging, it might be oscillating and jumping back and forth and never actually finding the minimum, depending on what the characteristics of the function are. There's generally going to be a maximum number of iterations that after it reaches that, it errors out and comes back to you and says, I've reached 100 iterations, or I've reached 1,000 iterations, I haven't converged yet, this is as good as I can do, basically. And in some cases, that just means that your optimization is just converging very slowly, but it's still converging. So you don't necessarily need to give up at that point. What you could do is go back to the function, and usually you can increase the maximum number of iterations and say, you know what, instead of having that max out at 50, make it 500, and I'm just willing to wait as the optimization converges fairly slowly. So those are some of the things to think about. Any questions about that? Okay, so there's a very, very brief section on starting values here, which is basically not because they're not important, but because we're going to see a bunch of examples of, we've already seen an example of starting values, and we'll see a couple more examples of starting values. And it's something that I've asked about on the problem set as well in a couple different places. So it can really matter both in, as we saw in Newton's method, it can matter in terms of whether or not you find a maximum versus a minimum. It can matter in terms of whether you converge to the answer or whether you diverge. And it can just matter in terms of how long it takes you to get to the minimum that you're looking for. So they are quite important. Okay, so there's also people who are doing, who study optimization, do a lot of analysis of different algorithms to see what is the performance of the algorithm and how quickly do they converge, and that basically amounts to figuring out what's the rate of convergence. So we're not going to do, in keeping with our theme here of being fairly practical in our perspective on optimization, we're not really going to do any theory here. But I just want to mention this so you guys see it. So the idea is, suppose we take suppose we take epsilon sub t to be the difference between my current estimate xt plus 1 and the one at the previous step xt. So, how am I framing this? So I guess I'm calling epsilon xt, okay, minus the actual true value x star. So this numerator is xt plus 1 minus x star, and this denominator is xt minus x star. So the question of convergence rates is basically, what's the relative size of the error at the t plus 1th iteration relative to the size of the error at the tth iteration? And the idea is to see whether or not this quantity has a limit where I raise the denominator to some power beta and see if that converges to a constant. So why is that a useful thing to think about? Well, if we have epsilon t plus 1, and I just rearrange that equation, and I have c epsilon t to the beta, let me just ignore the constant for a moment and just think about the raising this to a power. Well, if we're getting close to the right answer, then these errors should be getting close to 0, and they should be less than 1. So we're basically saying, well, suppose the error here were 0.01. If beta is greater than 1, for example, if beta were 2, then this is going to be something like 0.01 squared, which is 0.001. And this is saying this error is quite a bit smaller than this error. So if beta were 2, this is something that's converging quite quickly. As beta gets closer and closer to 1, then this error is not going to be all that much smaller than this error is, so it's going to be a method that doesn't converge very quickly. So we basically want beta to be as large as it can. And then once we get beta getting close to 1, well, then we would have that these two things are the same, but we're multiplying by some constant, so then we have to start thinking about what's the constant and how does that affect the convergence. So this is sort of like orders of magnitude, and when we're talking about linear algebra, we're talking about, well, it's order of n cubed, and in some cases we might look at the constant in front of n cubed and care about that, and in other cases we might just want sort of the broad brush of things of, is it order of n cubed, is it order of n squared, et cetera, et cetera. So somewhat similar here. So if beta is 2, this is called quadratic convergence, which is fast. If beta is 1, this is linear convergence, which is rather slower. So we can do this, a fairly straightforward analysis of the convergence rate for Newton-Raphson. And we're going to do a Taylor expansion of the gradient f prime at x star, and we're going to do the Taylor expansion around xt. So we're going to have f prime of xt, then we're going to have the first derivative of the gradient, so the second derivative we're going to include the third derivative in there. And we know from Taylor's theorem that we have some epsilon, we have some Cassi, is that Cassi? Do you remember what this Greek letter is? That's Cassi, okay. This one, I always get this confused with zeta because they're both very hard to write, I think. Okay, so this is Cassie. So there's some Cassie that's between xt and x star. Okay, the value based in terms of the Taylor expansion that we're doing. And we know that our Newton-Raphson uptake looks like this. So I can just rearrange terms and plug in and do a little bit of algebra. We won't bother going through that. But after you do that and the smoke sort of clears, this is the equation that you get. And that, the reason for doing the particular algebra that one does to do this is then one gets a form of the equation like we had, where we've got this over epsilon t to some power. And from this approximation, we can see that it looks like this. So here we've got epsilon t plus 1. Here we've got epsilon t squared. So that says that beta is 2 for Newton-Raphson. Provided this thing, so let's go back to the previous page. Provided that thing on that quantity on the right, well, provided both sides, but in particular, provided this thing has a limit as xt goes to x star. Okay, so that's basically the analysis of Newton-Raphson that tells us that beta is equal to 2. You can also see here that, again, this idea that things can go wrong when we've got that the second derivative is at or near 0, because here we see that, well, the error at the t plus 1th iteration is the square of the error at the tth iteration. That's equal to this quantity. Well, if this thing is close to 0, this thing blows up, and that says that this error is big relative to the previous error. So again, we see that we sort of see from a different perspective what goes wrong when the second derivative is it gets to be closer to 0. Okay, so any questions about that? Okay, so let's go just look at an example here. What we're going to do is just contrast Newton-Raphson and bisection. So Newton-Raphson being fast but having these dangerous characteristics to it, and bisection being slower but not requiring us to have 2 derivatives. It only requires us to have 1 derivative and not having some of these issues with Newton-Raphson diverging and having to evaluate the second derivative and possibly having that be small. All right, so what I'm going to do is I'm just going to do a silly toy minimization where I'm minimizing the cosine of x. Okay, so cosine between 0 and 2 pi is obviously minimized at pi, so that's the number I'm looking for when we actually look at the digits of precision in the answer. And we're going to do Newton-Raphson, and I'm going to start at 2 as the starting value. And we can see what happens. Well, it starts at 2. We know 3.14 roughly is the minimum. So it looks like it overshoots and goes over to 4, so it crosses over. Then it comes back, then it overshoots a little bit. But by the time we get to the 6th iteration, we're already at 3.14159, which we know is essentially what pi is. Okay? That we're already at 3.14 when we get to the 5th iteration. And when we look here, actually this looks like it got very, very close just in these couple iterations, because once we get from here to here, we see that up to 8 digits or so, the number's not changing anymore. Okay, so it didn't take very long for this to converge, even though it did a little bit of sort of back and forth as it started out. And then this is just me coding up what would happen if we did bisection. And I have to start out with a lower and an upper bound in this case. And I basically tried to set those, I basically tried to set those up to be sort of a fair comparison here. Okay, so I set up a starting interval, and then I proceed with my bisection. Then I take the current estimate to be just the average of the endpoints of the interval. And remember, I'm halving the interval at each of the steps when I'm doing bisection. And so when I do bisection, this is what I end up getting. So I start think I started out at 2 and something else, and the average of that was 2.78. Then I got to 3.17, 2.98, 3.07, 3.12. So this 5th or 6th iteration, remember this is with new Raphson where I was getting very, very close. And you can see I'm starting to get close, 3.14, but I'm not at 1.5 yet here. We're 3.147. So by the time I got to 3.1415, 1.5 or 1.59, I'm sort of down here in the 13th, 15th, 16th iteration. So you can see this is converging less slowly than Newton-Raphson. Okay, any questions or comments? Okay, so that's basically all I want to say about univariate optimization, and the idea is we're now going to switch to multivariate optimization and talk about a variety of different methods that we would use for multivariate optimization. Some of the things that can go wrong, some of the basic sort of intuition of how some of these methods are used, including how we use steps in single directions, so that we might make use of some of the kinds of tools that we've already seen for unidimensional optimization within a multidimensional context. Okay, so the basic idea is as the space gets larger, it becomes increasingly harder to find the minimum. We may be increasingly likely to have multiple minima that make it it might be a multimodal function that makes it hard to find the global minimum. And there can also be numerical issues that arise. So given the fact that as the dimension gets larger, it makes the problem increasingly harder to deal with. One of our strategies is actually going to be to take the large dimensional space and see if we can reduce it down to a smaller dimensional optimization. So another thing as I was walking over here, I was thinking about sort of what are some of the themes that we run across, and one of them, as I see it, is we want to try and marry computing power with being at least somewhat smart about using math to sort of ease the burden on the computer. So we don't want to have to be really, really clever about the math, or we want to rely on people who have been really clever about the math. We want to rely on the computer to some degree, but we may want to do something in advance that's going to ease the burden in terms of the actual computations. So in some cases, we can actually analytically maximize over some of the dimensions of the problem as a way to reduce down the dimension, and then do the numerical optimization in a lower dimensional space. In a likelihood context, this is called profiling and finding the profile likelihood. So I want to do a quick example of this. This is not going to be a hard derivation, but just to illustrate the concept here. Okay, so the general setting is we have some likelihood. We look at it and we say, you know what, I think I could actually maximize this mathematically with respect to some of the parameters, but then there are going to be some of the parameters where it would be a really hard or impossible maximization to do mathematically or analytically. So okay, suppose we have two sets of parameters. So suppose I'm trying to maximize with respect to theta now. I'm switching notation relative to I was using x before, in part because this is, often we're going to be talking about likelihood maximization. So the idea is, suppose if I look at my objective function, it's a function of theta 1 and theta 2, I see that I could actually fairly easily maximize that with respect to theta 2. So that's going to give us a theta 2 hat, but theta 1 is still going to be unknown in the problem. So I'm going to have a theta 2 hat that's a function of theta 1. So the idea is I could then plug this in to the objective function, and now I'm going to have some new objective function that's just a function of theta 1, and then I can throw that at a computer at some optimization routine and optimize with respect to theta 1. So let's see this in action in a particular case. So this would be the likelihood if y were a vector of observations. This is just a multivariate normal. This looks like a generalized least squares problem to us, right? We already saw that on the previous problem set. You actually coded up how you would do this. So we actually know what the analytical maximizer of beta is, if we, for the moment, don't concern ourselves with sigma squared and rho. So you've already, we already know what that is. We had that on the problem set. We know that beta hat, as a function of rho, it turns out sigma squared disappears when you maximize with respect to beta. It'll come back in a second. We know that beta hat is this expression, where this is a function of the data, and the x's end of the unknown row. Okay. So let's see how we'd actually do this. So I'm going to write out that likelihood. Okay, so I'm raising the variance component to a power. I have the determinant of the matrix sigma. This is a function of rho here. Then I have this is still a function of rho, right? Okay, I know what beta hat is. I could actually take the derivative and derive that, but that's also something that's well known that we could have just looked up as well. So I can now take beta hat and plug that in here for the beta here. Okay? And the basic idea is that it's a little bit hard to draw, so I'm sort of hesitating. Basically, if we're optimizing in a multidimensional space, we're basically reducing it down to optimizing on a subspace. And so if we're 2 dimensions, we're now reducing it down to optimizing across a line by plugging in the optimizer with respect to the other dimension. Okay, so if we plug in beta hat, what do we get? Well, I'm going to do this now on the log scale. So let me take logs, because for reasons that we've already talked about multiple times. So I'm going to have minus n over 2 log sigma squared minus 1/2 times the log determinant minus 1/2 y minus x, and now I'll plug in my my beta hat, which is still a function of rho, right? And now I've got sigma inverse of rho. Looks like I left out a transpose. I guess the thing I neglected to mention here is generally in the case of if we're maximizing the likelihood, we're just going to maximize the log likelihood. That's going to be equivalent to maximizing the likelihood. And since we usually frame it as a minimization, we're also often going to talk about minimizing the negative log likelihood. Okay, so now if I look at this, well, this is now a 2-dimensional optimization problem. So that's a lot better. Beta could have been quite large. So this is already a lot better than having optimized in the 2 plus p dimensional space where if beta had p different dimensions. And as long as we're sort of not naive about doing this, if you come to somebody and say, oh yeah, I'm optimizing this really hard problem, it has p plus 2-dimensional parameters and beta is really large, and they look at it and they say, you know what, you're just basically doing a regression. You're like, oh, of course, I can do this in a lot smarter fashion. I don't need to do the numerical optimization in p plus 2 dimensions. Okay, so this is now a 2-dimensional optimization. We actually can go even a step further. If we look at this, we say, you know what? Actually, I guess I left out the, this was over sigma squared here. Right, I had sigma squared lowercase sigma times capital sigma inverse. I'm just going to pull out the sigma squared, and that's going to go into the denominator. So if I look at this, and I stare at it for a second, what do I realize? Well, this is really not that much different than doing maximum likelihood with respect to the lowercase sigma squared in just a standard maximizing a normal likelihood. So I should be able to maximize with respect to sigma squared analytically as well. So let me take the derivative with respect to sigma squared and maximize with respect to that. Okay. This thing doesn't involve sigma squared because the sigma squared got pulled out here. Now I've got sigma squared here. I take the derivative with respect to that. I'm going to get plus 1/2 times that quantity up here over sigma squared, and I'm going to set that equal to 0. You can just write, I'm just going to use a little bit of notation and say, well, this is just some sum of squares term. So I'll just call this sum of squares of rho. And now if I solve for sigma squared, well, sigma squared hat is just going to be the sum of squares with respect to rho divided by n. Okay? So this is not that much different than the usual estimated maximum likelihood estimator for sigma squared, where we divide some sum of squares by n. The unbiased estimate is divided by n minus 1, but the MLE is divided by n. That's what we get here. So now I'm going to plug sigma squared hat back in the places where it appeared in this objective function and derive a new univariate objective function where I'm only going to have to maximize with respect to rho. So now if I plug sigma squared hat back in, I'm going to get minus n over 2 log of this sum of squares of rho over n minus 1/2 log of, I should have put a rho in here, sigma of rho. It's kind of fun what happens here. Fun, yeah, okay. That sigma squared over rho over n, well that plugs in here, the sum of squares. The two sums of squares cancel out and I just get minus 1/2 n. So this term is not even going to play a role in the maximization anymore. Okay, so I've gone from p plus 2 dimensions down to p plus 2 dimensions down to 2 dimensions down to 1 dimension. This is now going to be a pretty easy numerical optimization. Once I get rho hat, what do? Well, I sort of walk my way back up. Once I know what rho hat is, I know what sigma squared hat is. And once I know what rho hat is, I also know what beta hat is, because that's also just a function of, that's also just going to be a function of rho. Okay, any questions about that? Okay, so now let's talk about Newton-Raphson in, so the idea is we might find a nice way to reduce the dimension of the problem. Often we're still going to have the problem being a multivariate optimization that we need to do numerically. So if we write out what Newton-Raphson is in the multidimensional case, we get that xt plus 1 is xt minus the second derivative, but now the second derivative is a full matrix, which I wrote out the notation for that on the first page of the section notes. So instead of dividing by it, I need to take the inverse of that, and then I'm going to multiply it by the gradient vector. Okay, so this is just the multivariate optimization of what we've already seen. If we write it in slightly different notation, it's the Hessian, the inverse of the Hessian, which is the same thing as this, just different notation, multiplied by the gradient vector. Okay, so we can think about in multiple dimensions what are the things we need to think about. Well, we've already talked about what do we need to think about in one dimension for Newton-Raphson. We need to worry about what are good starting values. We need to worry about divergence. We need to worry about when if the second derivative is too close to 0 and we end up dividing by something that's 0, that relates to the idea that we might end up having this thing diverge. All of those things can arise here. The variation that arises here is instead of trying to divide by 0, we're trying to take the inverse of a matrix. So what do we need? What would we need to happen for this? We need to have this matrix be invertible. In essence, because this is a symmetric matrix, it's basically amounting to have it being positive definite. So the same sorts of things can arise in multiple dimensions if the Hessian is not, as arose in one dimension. In this case, if the Hessian is not positive definite. Oftentimes the function is approximately going to be locally quadratic, so the Hessian is going to be invertible, and there are ways that you can basically get a Hessian and then modify it by basically adding on the diagonal, and that will sort of stabilize the calculations. Okay, so let's actually see an example of doing this. I'm going to do this with a least squares problem, and I'm going to use this both to sort of illustrate Newton-Raphson in multiple dimensions, but also to talk about finding starting values and give a little bit of intuition for some of the ways that people will sometimes think about finding starting values. So this is basically a nonlinear least squares problem. Assume that these errors are normal, or that we're willing to assume that they're close enough to normal that the objective function we want to find is basically, or the objective function we want to optimize with respect to is just a sum of squares criterion. So I'm just going to be trying to minimize the sum of yi minus beta 0 minus beta 1 e to the minus ti over beta 2. Did I get that right? Yeah. Squared. Okay, so at least in this parameter, this is a nonlinear least squares problem. So let's just look at an example here. Okay, so I'm just going to use an example of some data on changes in somebody's weight over time, and we're going to see that if we just look at the data, so I believe this was just for one person, but it's possible there were multiple people in this data set. I'm not, although then it probably wouldn't make sense that they would all be on the same scale here. So I imagine this is just one person over time. So if we look at this, we can see, well, that doesn't look like that doesn't look particularly linear, although it's not crazily different from a linear curve. And somebody came along and said, well, maybe this mean function, if I take out the minuses here, that might be a reasonable mean function to fit something that has this curved shape to it. So the idea is, well, let's try and fit the nonlinear least squares problem that I've set up to these particular data and try and find the best values of beta 0, beta 1, and beta 2. Okay, so if I did actually just do a linear fit on this plot, actually maybe doesn't show up very well for those of you in the back, but I get this fit, which is not all that great a fit for these particular observations. Okay, so part of the reason to go through this example is just to start thinking about how do I get starting values and how do I sort of approach a problem in sort of a pre-processing stage to think about what would I do to get some starting values. And I don't know that there's a recipe for this. It's just sort of often it's a matter of sort of sitting down, looking at the function you're trying to optimize, and trying to come up with some plausible values for the parameters. Well, so what am I going to do here? Well, my thought process was, if I look at this, I know the times are sort of on the scale of 0 to 250. So that probably suggests that beta 2 needs to have an order of magnitude something like those kinds of values, since I'm dividing the times by beta 2. So what if I just take beta 2 to be the midpoint of the number of days, or so roughly like that? So I'm just going to set beta 2 to be equal to 1. And then once I have a value for beta 2, this whole term is going to be fixed, because the TIs are the covariates, those are the times, which are known. And then I could get starting values by basically just doing a regression of y on these values, one for each of the times, and that would give me starting values for beta 0 and beta 1 that are consistent with the value that I've chosen for beta 2. So sometimes it's a matter of sort of saying, well, I can sort of get a handle on this parameter by thinking about it this way, and once I have a handle on that parameter, I can maybe do some other steps to try and get a handle on what the other parameters might be. Okay, so what I'm going to do is I'm trying to follow this recipe. What if beta 2 were 100? Well, then that new covariate is, did I write that wrong? Oh, sorry, that was 2 rather than E. If I were doing a linear regression of yi on the 2 to the minus ti over beta 2 values, then when I plot those, I should see that there's a roughly linear relationship. So suppose I do that. So I'm just going to take beta 2 to be my starting value to be somewhat arbitrary value. And I'm going to plot the relationship between the covariate and the observations, which are the weights. Yeah, it doesn't look too bad. That looks sort of linear. So maybe I'm willing to proceed with beta 2 being initialized at 0. So now I'm just going to do a linear regression to get the weight on the 2 to the minus days over beta 2. I think this I just allows me to insert an expression here without having to create the variable as a named variable. And now I can just set my initial values for beta 0 and beta 1 from having done that regression. Okay. So let's actually plot. I can now basically do a sanity check of what I've come up with as my initial values by plotting what does the regression line look like with the initial values that I've come up with, and see that it's not too terrible. Okay, so there are the data again, and with this recipe that I've just gone through, it's not really a recipe, it's just this thing that I've gone through to come up with beta 0, beta 1, and beta 2 starting values, I get this red curve. Well, it's obviously not, presumably not the best fit, but it's not the world's worst fit to these particular data. So I may be happy at this point with then starting with these values and doing my numerical optimization from that point on. Okay, so any questions about what I'm doing here or the sort of thought process involved? Okay. All right, so what do I need for Newton's method? Well, I need to calculate the gradient and I need to calculate the second derivative. So I could sit there and by hand work out first derivatives and second derivatives. I don't know about you, but I'm terrible about making mistakes when I take derivatives by hand. Like, you know, I always leave something off. Like, I know what I'm doing more or less, but it's just sort of tedious to have to go through the procedure of doing it, particularly to have to do it for second derivatives, right? So we're going to see in the unit that we cover in a couple weeks that we can actually take derivatives symbolically using computer programs. Mathematica is particularly good at it, but you can actually do it in R to some degree as well. So I'd like to take a derivative of this with respect to beta 0, beta 1, and beta 2 and second derivatives as well, right? Well, R will allow me to fairly easily take the derivatives with respect to this quantity without the sum. So I'm going to ask R to give me first and second derivatives with respect to this inner quantity, and then I'm going to insert the summation myself, sort of into the expression it gives me. So I'm going to write out the expression. This is going back to some of the stuff we saw in Unit 6 about actually writing out an expression as opposed to having R evaluate the code itself. So I'm using quote here. And now I'm going to call the deriv and deriv3 functions. Deriv3 is basically the same as deriv. I don't know why it's called deriv3, but it defaults to giving us the Hessian, the second derivative matrix, by default. So this is just to give an example of what that will do. What it'll do is it'll sort of give you this this long expression where it'll come up with some interim expressions, these dot expr3 and 6. And then it'll say, well, the gradient with respect to beta 0 is minus 2 times this interim expression, and the gradient with respect to beta 1 is minus 2 times the 3 and the 6 expressions, and so on and so forth. So it's sort of doing these derivatives sort of piecewise, and then it sort of pieces them back together to get the derivative of the resulting expression. So deriv is fine. I actually need the Hessian, so I'm going to use deriv3, and that'll by default give me the components of the Hessian, as well as the components of the gradient. You can see this has a similar form. The Hessian with respect to beta 0 and beta 2 has this form that's a function of this piece of the Hessian. Oh, I see. It looks okay. So it's basically saying, well, this thing is symmetric, so the Hessian with respect to beta 0 and beta 2 is the same as the Hessian with respect to beta 2 and beta 0. And that's 2 times this expr16, which has presumably just disappeared off the screen. So it's a little bit ugly, but these are the things we'd have to write down if we were doing it by hand as well. So I'm glad I can rely on the computer to have done that. So I'm going to write out what the objective function is, that least squares function, and I'm going to now write out my derivative function, my f prime function, using those terms that I calculated that were calculated from the deriv function, but now I go in and make sure that I put back in the summations that I need that were left out of when I did the derivative symbolically. And then I do the same thing with respect to the second derivative. I need to do a little bit of pre-processing because I want to be able to have the function be a function just of a vector of values, but then it's easier for me to work directly with beta 0, beta 1, and beta 2, so I'm going to decompose the vector here. Okay, so basically, long story short, I've created functions for the objective function, the gradient, and the Hessian, in part relying on R's numerical analytical differentiation capabilities. And I've got my starting values, and now I'm just going to code up Newton's method. Well, as long as Newton's method works and the derivative is as long as the Hessian is invertible, is positive definite, then this is fairly straightforward. I just do solve. In this case, I'm not explicitly getting the inverse. I'm using what we talked about last unit. I'm doing solve against the gradient that comes from against the vector that comes from calculating the gradient. I have a little bit of code in here that just checks in terms of what happens if things go awry. I have some code that should work if the thing were not numerically positive definite using the pseudo inverse, but I don't actually have that set to work in this case. And so if I go ahead and do that, I can check if there is a built-in nonlinear least squares optimizer in R, so I can go ahead and look and see what parameter values it gives me. And I should see that the x values that I got from doing it myself, these were the values. Remember, my starting value was up around 100, and these were the beta 0 and the beta 1. And you can see that these are the iterations, and after a while it's going to converge. It looks like it's converging, and indeed it does converge to the same values that R's nonlinear least squares gave me. So let's quit there, and I'll say a few more words about this example when we come back, and then we'll move on to some other methods next time.